In this session, let's try looking out some of the important formulas associated with level annuities. As we all know, that annuity is nothing but it's a regular series of payments, right? It's a regular series of payments or receipts at equal intervals of time. It's a series of payments or receipts at equal intervals of time. Now, with this regular series itself, if even equal payments are coming up, even if the payment amounts are also same, the intervals are same, fine. Even if the payment amounts are also same, equal payments are also present, we call those as level annuities. The payments are also same at each period per a predefined set of periods. So those are called as level annuities, and within those level annuities also we can talk about a regular annuity versus annuity due. Regular annuities are where the payments are made at the end of the period. So the period could be year or month or whatever it is. The payments are made at the end of each of the period. Whereas when we are talking about annuity due, the payments are made at the beginning of the period. Both are level annuities only, but the payments are made either at the end of the period in case of regular annuity or at the beginning of the period in case of annuity due. So probably if we are talking about a uniform value of 1 coming at the end of each of the years, a value of 1 coming at the end of each of the years, let's say for n years. What is the present value? So this I will discount by 1 plus I, this I will discount by 1 plus I squared and so on. So probably this is nothing but V, this is V squared, this is V cube, and probably it is going to V per n. So the present value of all these things, right, that is represented by our symbol called AN. It is the present value of an annuity, a regular annuity, the present value of a regular annuity of value 1 coming at the end of each of the periods over 1 for each of the n periods. So if we just try applying the geometric progression formula on the top of this, sum of n terms of a geometric progression, first term into 1 minus the ratio to the power number of terms n divided by 1 minus the ratio. So this becomes V into 1 minus V power n divided by 1 minus V. So probably if I try writing, instead of V I will write 1 by 1 plus I only for the first part. I'll keep 1 minus V per n, and here also 1 minus V also I'll write 1 by 1 plus I. So probably it is coming out as a simplified form 1 minus V power n divided by I. So sometimes people keep this as a formula. So finding out AN, which is nothing but the present value of immediate annuity, we'll write it as 1 minus V per n by I. Here, a few more quick additions I would like to do. If the same question turns out, so if you remember this one, probably a lot of questions can be handled quite quickly using this concept itself. The moment you know this is the present value of a regular annuity, Okay, whenever the question is about find the present value of immediate annuity, right? So now let me start writing it. The present one major result which you have to remember is the present value of regular annuity. The present value of a regular annuity will come out as 1 minus V power n divided by I. Now, annuity due. So this is actually represented as AN. But the same logic when I use it for annuity due means all the payments are coming one period in advance. So basically it becomes 1 minus V power n. Whenever we are talking about annuity due, we use the word, we use the rate of discount rather than the effective rate of interest. Now extending it a little bit more, if I want AN, present value of the annuity, but the payments are not done at the end of the year, but the payments are done on a peathly kind of a basis. It is nothing but when the payments are done on a peathly kind of a basis, I can very well use the same formulas 1 minus V power n by IP. So the same way when I am looking at peathly annuity where the payments are made on a peathly basis in advance. Again the same logic comes. This is becoming 1 minus V per n by dp. So if we see there are so many, if I remember one formula, I can try looking at bringing out the relationships between all these formulas also. So in a way, probably I can write this. In a way, I can write this. So one more logic which we can look at in this case is probably if the payments, if I'm looking at okay, an is 1 minus V per n by d, right? So if I try to find the relationship between an and probably an with immediate, if I'm doing one divided by the other, an divide or probably an divided by an. If I am looking at these two things, it is nothing but 1 minus V per n by d divided by 1 minus V per n by I. So it is nothing but I by d, and d we know the relationship between d and I. D is nothing but I by 1 plus I. So obviously it is coming out as I by 1 plus I, overall going as 1 plus I. So in a way you can very well prove one more relationship, which is an equal to 1 plus I times an. So one more important relationship you can bring out, the immediate annuity. Present value of immediate annuity is nothing but 1 plus I times the present value of a normal annuity. The same logic again goes in all the cases. So that's one more relationship which we can derive. And at the same time, okay, let's look at if I want a n minus 1. Let's try out a n minus 1. What would have been the formula for a n minus 1? 1 minus v power n minus 1 divided by I, right? Now I know this, so if we are looking at, let's say, an 1 minus v per n divided by d, d is nothing but I by 1 plus I. So you take 1 plus I to the numerator, 1 plus I into 1 minus v power n divided by I. So you look at this, you multiply this 1 plus I into 1, which is 1 plus I, minus 1 plus I into V power n. V power n is nothing but 1 by 1 plus I to the power n. So this becomes V power n minus 1 divided by I. So now again take this out. I by I is 1 plus 1 minus V power n minus 1 by I, which is nothing but 1 plus a n minus 1. So one more result you can derive. A n with an immediate annuity is same as 1 plus a n minus 1 a regular annuity. So you can try building out various kinds of relationships between these variables the moment you know how to calculate the first one. Sometimes we can, so the typical thing is the AN numbers for different rates of interest are directly obtained from the actuarial tables, but even if they are not available for some particular rates of interest, non-common rates of interest, we can very well use these kind of formulas, 1 minus V power n by I or D or kind of formulas to typically find out the present value of all those present values of all those different kinds of level annuities. Now, the next important thing I would like to look out is for computing the accumulated values. Now, simple thing is anytime accumulated value is nothing but present value into 1 plus I to the power n. That is what is the accumulated, which means in case of our regular annuity, let's say 1 minus V power n by I into 1 plus I to the power n, that is the accumulated value. Probably in some cases, as a part of a simplification, what will happen is this becomes 1 plus I to the power n. V power n into 1 plus I to the power n is nothing but 1 divided by I. So this will become the accumulated value. Now the same logic whenever we have D, which is so the accumulated value generally is denoted by S. Present value is denoted by N. Accumulated value is denoted by S. Now when I am talking about this, obviously the I is going to become a D. So the logic still remain the same. So accumulate regular accumulated, this is accumulated value of a annuity due, accumulated value of a regular annuity. Again this goes as nothing but D by I by D, which is again 1 plus I. So obviously we can write accumulated value of an annuity due is 1 plus I times accumulated value of a regular annuity. So once we try to understand these kind of basic numericals, now let's see when I try writing out, okay, this is the accumulated value of the regular annuity. Now probably if I try instead of Sn, I will write this formula 1 plus I whole power n minus 1 by I. Look at this, what it is happening. It becomes 1 plus I to the power n plus 1 minus of 1 plus I divided by I. On a simplification, it is becoming 1 plus I to the power n plus 1 minus 1 by I minus of I by I, which is 1. Right? Minus of I by I, which is 1. So this is nothing but it is becoming, this part is Sn plus 1 minus 1. So we can try converting into various forms once I know the present value and the accumulated values of the various level annuities. Now we know one more important relation. We know that AN is nothing but 1 minus V power n by I, and AN annuity due is 1 minus V power n by D. Similarly, Sn, the accumulated value, I multiply it by 1 plus I, 1 minus V power n by I multiply it by 1 plus I. Then similarly for annuity due also Sn 1 minus V power n by D, I multiply by 1 minus I. The other form, this is end of the period, this is beginning of the period. But the third form is throughout the period, which is like a continuous. So that will come out as A bar n. A bar n nothing but instead of I and D, I'll put deltas here. That's one more relationship. S bar means like a continuously payable kind of an annuity. I will again multiply all this with 1 plus I itself. Now again another set of relations can very well be derived, because delta is nothing but, as we know, it is log 1 plus I. So we can try expressing again. So if I want A bar n divided by an, it is nothing but I by delta, right? I by delta is the A bar n. So probably you can very well say A bar n is nothing but I by delta times an, or similarly S bar n is I by delta times Sn. So all these kinds of relationships can quite comfortably be derived. Again the same thing, even if it is a P3 kind of compounding also, nothing. In the denominator instead of I will use IP, instead of D I will use DP. So getting some level of comfort level in these calculations will make things more and more easier for you, right? So again the same logic. So let's say if you are talking about, let me use one more important relationship, right? When I am talking about ANP, what did we say? In a regular ANP we said 1 minus V per n by IP, but a normal AN we said 1 minus V per n by I. So logically also, if I am doing ANP by AN, it is nothing but I by IP. So in a way I can find out ANP as I by IP times AN. So the moment you start working out with these relationships, things become more and more comfortable. Similarly, okay, this is the formula for AP, ANP. Now, immediate regular annuity due, if I am looking at ANP, the formula would have been 1 minus V per n by dP. So again, when I am trying to write, right, AN ANP immediate by ANP regular, this is nothing but IP by dP, right? This is coming out nothing but IP by dP. So again it is working out to IP by dP is nothing but, so this, if I leave it as IP, this dP is nothing but I by 1 plus I to the power 1 by P. So it is typically working out as 1 plus I to the power 1 by P. So from here you can very well get AN immediate annuity on a P3 base, annuity due on a P3 basis is nothing but 1 plus I to the power 1 by P into an annuity due regular annuity on a P3 basis. So basically all these are revolving around one single formula, which is the regular annuity where the payments of one are being paid at equal intervals of time in future. Now, one more variant of that regular annuity is the perpetuity. Like the same 1 is paid not for n periods but for infinite. So the present value is nothing but v squared v cube up to infinite terms. Now we know sum of infinite terms of a geometric progression is nothing but a by 1 minus the common ratio. So if I try to write this a, which is v 1 by 1 plus I minus 1 by 1 minus v, again 1 by 1 plus I, this is getting simplified to 1 plus I minus 1 I again by 1 plus I, which is coming out to 1 by I. So the present value of a perpetuity is 1 by a regular perpetuity is 1 by I. A perpetuity due, generally written as infinite here, I'll write it as 1 by D. Now the same logic, a P3 payment of a regular perpetuity, I'll make it 1 by IP, and similarly P3 payment of a perpetuity due, I'll write it as 1 by DP. So these are the different forms of formulas I need to be really comfortable with so that I can use them quite comfortably in this context. Right? These are the various. So when I'm talking about an annuity, my intention is just plainly look out for some equal amount received at different points in time in future, and I am trying to compute the present value of all of them. So trying to compute the present value of all of them resulting in AN, and immediate annuity due is resulting in payments coming one period before. So we are trying to find out the payment. We are trying to find out the present values of regular annuity, annuity in advance, P3 payments in advance, P3 payments in regular, which is arrears, continuous payments. Similarly, we tried finding out the accumulated values also in all those situations, and finally we have even looked out for the present values of perpetuities, level perpetuities itself, again either on an annual payment basis or a P3 payment basis. So all these typically are the various numerical formulas that we need to be comfortable with. If at all we have to solve some kind of cases relating to the annuity payments or receipts. So using these concepts, we will typically look at some numericals. We'll try to take up a few examples to demonstrate all these concepts, and using these how we compute the present values or future values of a series of level payments. So with that as the base, let's get started into the usage of a few numericals for the same. All right. In this one, let's look out for a simple numerical concerning the level annuities. Right, equal annuity payment that is being made. So look at this numerical. An investor deposits 13,160 today. So cash outflow wise, at 0th period there is 13,160, and then withdraws level annual payment starting 1 year after the deposit was made. So he has been withdrawing some money immediate, so which means at the end of 1 year he is withdrawing something, 2 years he is withdrawing something, up to 8 years he withdraws something. So let's assume that he has been, because it's a level withdrawal, he has been withdrawing the same X for 8 years. Immediately after the 8th annual drawing, the investor is still left with 3,748 in the account. So it's as good as saying whatever has been deposited, the present values of whatever has been withdrawn, the present value of the inflows should be equal to the present value of the outflows. In a way, it is like writing it like this: 13,160 plus X into V, because first X is drawn after 1 year. X V squared second x after 2 years, x v cube plus so on x v power 8 plus 3748, which is left at the end of 8 years also, v power 8. This entire thing should be equal to 0, or the present value of the cash outflow should be equal to the present value of the cash inflows. This is what is the simple definition mechanism. So from here comes the simplification. This part is nothing but a level annuity. So x is the amount, v plus v squared plus so on goes as A8, and this A8 is something which I would compute at 5% interest rate plus 3748 into v power 8, and here we are taking the annual interest rate to be 5%. Okay, let's simplify that process now. If I say the annual interest rate is 5%, what is so I is 5%, right? Annual rate of interest I is 5%. So from here, what do I get as V? 1 by 1 plus I. So this V is 0.95. Then I need V power 8, which is nothing but this number raised to the power 8. This is my V power 8, and I will take 3748 into V power 8. 3748 into V power 8 comes out to this number multiplied by 3748. So this is 2 pi 36. So I take it to the other side. It comes out like 13,160 minus 2,536. So this is nothing but x times 8 at 5% interest rate. This is going to be 10,623.21. So I can find out what is this value of A8 from the actuarial tables, compound interest notation, 5% interest rate. I can find out the value of A8. The value of A8 is 6.4632. So A8 is 6.4632. From here I can find out my value of x, which is 10,600 divided by 6.4632, and the entire number is working out to 1643.64. 1,643 rupees 64 paisa has been made over the 8-year period, which is symbolizing this level annual withdrawal. So such kind of simple numerical, word based problems, we have to convert them into notation kind of mechanism, which can help us in simplifying the calculations quite comfortably. Alright, let's look out for a basic numerical with respect to level annuities, wherein we are talking about someone who has deposited 5 lakhs or 500,000 in a bank, withdraws a level amount at the end of each quarter, starting 3 months after the deposit is being made. So probably some amount X is withdrawn after 1 quarter, so probably this becomes XV per 0.25. Similarly, another X is withdrawn after 1 more quarter, making it XV per 0.5, and so on up to the 48th withdrawal. So it is becoming XV power 12. Sanjay withdraws the balance of 75,000 from the account. So all we can write in the notation form Probably all we are saying is the present value 500,000 is X. This is X is some quarterly. So if I multiply it with 4, it becomes annual. And like that he is withdrawing for a period of 12 years. And at the rate of 6% per annum. And this is withdrawn on a quarterly basis. So basically this number is 4x 812 on a quarterly basis at the rate of 6%. So probably this number can get improvised 4x 812 I divided by I4 into, that's it, I divided by I4, and all of them are at 6% rate. So from here I should be able to find out this plus 75,000. We are talking about V power 12. At the end of 12 years, it is being withdrawn. 7,000 is being 75,000 is being withdrawn. So our final equation for a solving purpose is 500,000 equal to 4x 812 I by I4 plus 75,000 V power 12. So we can take I equal to 6% and then start working. I 6%. So V will be 1 by 1 plus I, which is this much, and V power 12 will become this number to the power 12, which is this. So RHS second term. Second term of RHS is 75,000 into V power 12, that is the second term. So the LHS minus RHS second term will give me 500,000 minus the above one, which is giving me 462,000. And I require A12, I and I4. So I require first I4, which I can calculate 4 times 1 plus I to the power 1 by 4 minus 1. This is what is the value of I4. So I4 in this case has come out to almost 5.87%. So from here I can work out. I also require A12 here. A12 at 6% compound interest. I will look out for A12 at 6%. I want A12 working out to 8.3838. 8.3838. So from here I can find out the value of X, which will work out to this being the first value, numerator, divided by 4 times, okay, A12 times I by I4, I divided by I4. So this is telling me that my X is 13,498. So every quarter I'm paying somewhere around 13,400. I mean, this person is withdrawing somewhere around 13,498 rupees, which will leave at the end of 48th quarterly withdrawal a balance of 75,000 will be left in the account, which can very well be withdrawn. So this is a very basic numerical with respect to level annuities, wherein a simple forming of the equation is very much necessary to solve these kind of problems. Now let's look at one more numerical associated with the present value of annuity computation. Right, again different payment, different points in time for different time periods. All I need to find out is the present value of the same. Now let's look at this situation. Combine the present value of an immediate annuity payable quarterly in arrears. So at the end of every quarter there is some payment that is being made. 9,300 per annum. 9,300 per annum for the first 5 years and 3,220 per annum for the next 4 years, but all of them are paid quarterly itself, and even a lump sum is paid on at the end of 9 years. So if I have to look at their total present value, all I could say here, it is given that the interest rate is 7.5% per annum. So I can convert it into quarterly, because this is convertible quarterly itself. So 7.5% divided by 4, that is the effective quarterly interest rate. So the effective quarterly interest rate I can take, and probably I can try finding out the present values of the same. Or probably, if at all I have to use this mechanism, it is more like, okay, 9,300 by 4 is what I get every quarter for the first 5 years. So the first payment is like 9,300 by 4 into V. The V right now I will take it as 7.5 at the rate. For the corresponding I will take it as 1.75% or 7.5% divided by 4. I'll take it as 7.5% divided by 4. So the first payment is 9,300 by 4V, 9,300 by 4V squared. And now this is for 20-year payment. So the last one would be 9,300 by 4V power 20. Because we are talking about quarterly payments. And after that, there is going to be a 3,220 per annum. So 3,220 by 4 V power 21, 3,220 by 4 V power 22, and so on. We have it up to V power 36, 3,220 by 4 V power 36, and finally we also have 19,540 V power 36. So this is what will be our series of payments, and all of them being used at the rate of 7.5% per annum convertible quarterly. So it's as good as probably if I had used a spreadsheet for the same over the 36-month period, just to verify. Over the 36-month period, if I am using the spreadsheet, my cash flows are like this. The years 1 to 36, for the first 20 quarters, my cash flow is 9,300 divided by 4. So 2,325 is the payment for the first 20 quarters, and after that it becomes 3,220 by 4. 805 will be the payment for the remaining quarters. And now all I can do is the present value. If I require, all I am doing is the cash flow divided by 1 plus the interest rate for the period is 7.5% divided by 4, because I am talking about convertible quarterly, and thus I am converting it as effective quarterly rate itself. So the present value for each of them, each period, I am discounting it by their corresponding time period. So this happens to be my present value, and the final, there is the 19,540 that is paid on maturity. So even the last period I add up to this 805, I can even add up 19,540, making it 20,345, and from here I can compute the total present value, which I am talking about as the summation of all the various present values, giving me a value of 56,104. That happens to be the present value total if I am going with the spreadsheet. But the same logic as I have used here, if I am using a geometric progression, my value would have been, the present values would have been, the first part 9300 by 4 is my present 9300 by 4 is the regular amount, and we are talking about v plus v squared plus so on up to v power 20. Had this interest rate been an integer, 7.5% by 4, here it's not an integer and I cannot refer to the actuarial tables. Otherwise I could have taken this directly as 820 and I would have completed the process. But because I don't have that kind of a flexibility, because the I here is 7.5% by 4, which is not an integer, so probably I am using the geometric progression again, 9300 by 4, and the sum of 20 terms of a geometric progression, v into 1 minus the first term a into 1 minus r power n divided by 1 minus r. So this is what is the approach which I am using. V into 1 minus v power 20 by 1 minus v, first of all. So for the first 5 years, right? We'll break it down into 3 parts to do this computation physically. So I is 7.5% by 4. So based on this, I should be able to compute V. V is 1 by 1 plus 1 by 1 plus I. That is what is my V. I need V power 20 also for this numerical. So I'll take this number to the power 20. This is my V power 20. So from here I can get my first 5 years. PV for the first 5 years is 9300 by 4 multiplied by V multiplied by 1 minus V per 20 divided by 1 minus V. So the first 5 years is working out to 38,000. Then the same logic now if I apply for the next 4 years, 3220 by 4, this is V21, V power 21 to V power 36. Again I can use a geometric progression. The first term V power 21 into 1 minus V power 16 divided by 1 minus V. So this becomes for the next 16 period. So I require V power 21 as well. This is V power 21, and I also require V power 16. So this is my V to the power 16. Alright. So my next 4 years, this is going to be 3220 by 4 multiplied by V per 21 multiplied by 1 minus V power 16 divided by 1 minus V. So the next 4 years is going to be somewhere around 7,613, and finally there is a 19,540 V power 36. So if I compute V power 36, this is this number to the power 36. So this is V power 36. So the final payment, if I look at it, it is 19,540 times V power 36. So this is around another 10,000. So if I find out the total present value through this mechanism, it is the present value of the first 5 years, then the next 4 years, and finally the final lump sum payment. Again working out to 56,104.21. So whatever is the mechanism that I am using, it has to be more and more conceptually driven kind of a mechanism. So even though it takes some time, it gives us the comfort in terms of solving things quite easily. Right? Now that I know that this is my present value, the another thing that I am supposed to look at is calculate the amount of level annuity payable continuously for 9 years. Continuously. Level annuity payable continuously for 9 years, having the same present value as the above. So that what is the present value as of above? 56,104.41. So that is the total present value of the above calculation. We are talking about the level annuity, means the same X being paid every year. So because we are working on quarters, we are talking about the same X by 4 being paid, right? The level amount that has to be paid is what we are finding out, and this in terms of continuous payment. So it would more come out like for A9 on a continuously payment basis, what is that particular value of X? So in fact this will not be A9 because we are talking about quarterly payment, so this would be A36. So X by 4 A bar 36, which is like a quarterly payment. Again I am looking at it on a continuously payment basis per P. This is the periodic payment. The periodic payment on a continuously payment basis for the 36 quarters, and the quarter is the effective rate of interest of 7.5% by 4 itself, right? So this we also have a formula A bar 36, which is 1 minus V power 36 by delta, right? The A bar 36 we have 1 minus V power 36 by delta, so probably X by 4 into 1 minus V power 36 by delta is what will be the value. So from here I can find out my X, which is that level annuity as 56,104.41 multiplied by 4 delta divided by 1 minus V power 36, and delta is log 1 plus I. Right, delta is log 1 plus I. So probably I can very well go forward 56,104. So if I want the level annuity X, I can take it as 56,104 multiplied by 4 multiplied by delta. Delta is log 1 plus I. This is the delta, and this entire thing we are dividing by 1 minus V power 36. V power 36 is this one. So finally it is coming out that the level payment in this scenario is 8,548 per year. 8,548 rupees 87 paisa will be the level annuity payment, so that both of them will have the same present value. And now from here is talking about find the accumulated value for the first 7 years payments. So the first 5 years it is so in the second model, if I want to find out the accumulated value, every quarter there is 8,000, every year there is 8,548.87 that is paid. So from here I can compute on a annual on a quarterly every year on an average 8,548 is being paid. So this we can use for computing the accumulated value, whereas here for the first 5 years we will accumulate it at the rate of 5 years at the rate of 9,300 per year, whereas for the next 2 years we will look out at 3,220 per year. So we can put the same as a part of our calculations. So simply moving forward, we can very well use 8,548.87 by 4 into S 7 years, right? So S28 on a continuous basis we can directly find out, and on the other side for the first one we can take 9,300 by 4 probably for the first 5 years. So probably I can take it as 820, and we can also take the next 4 years 3,220 by 4 V per 20 into A8. This will give me the total present value of these payments, and probably you can multiply them with 1 plus I to the power 28 to get the accumulated value. As we know that from the present value we can compute the accumulated value by multiplying it with that particular time period and the effective rate of interest for that period. So instead of directly finding out the future value, we can find out the present value and then accumulate it by using 1 plus I to the power 28. So whichever the one that gives us the higher value is more preferred in our case. Alright. Now we can find out the present value of a perpetuity. As a definition, we know that perpetuity is nothing but it's an annuity payment forever. There is no time period, there is no specific maturity period, or there is no specific time period during which the payments are being made. It is a perpetual payment. It is a forever payment of an equal sum of money for the entire life. So for those things, we also have seen the present value is nothing but the annual payment amount, whatever it is. If I want the present value, the annual payment amount divided by the effective annual interest rate. That is what was the present value of the perpetuity. But of course, if the payments frequency is different, then probably even the I has to be different. Like in this case, a bond pays a coupons in perpetuity on 1st June and 1st December. Okay, the annual coupon rate is 5.2% per annum. But it is paid on 1st June as well as 1st December. So it is actually paid 2 times in a year. Right? So when I have to compute the present value, it is better that I take whatever is the payment 5.2 divided by I. Instead of I, it's better that I take I2. Instead of I, it's better I take the I2, which is nothing but just as an equation, 1 plus I should be equal to 1 plus I2 by 2 whole squared. So just to get that comfort level, I2 for us is nothing but 1 plus I to the power half minus 1 and this entire thing multiplied by 2. So first, from an effective annual rate of 9%, so once I know that my I is 9%, I will look out for what is the value of I2. I2 for me comes out using this formula 2 multiplied by 1 plus I 1 plus I to the power zero point 0.5 minus 1. So this is giving me the I2. I2 is working out to somewhere around 8.81%, right? So I can very well find out my PV, which is payment 5.2 divided by I2. So probably if I take the payment, which is 5.2 for every 100, so overall it is working out to the present value of perpetuity is the payment divided by I2. So it's almost payment divided by I2. It's somewhere around 59.04. That is the present value of this perpetuity. But the drawback is this is as per the 1st June, right? Because if I am assuming that the payment is due 6 months later, that is where this value is, right? Because we are working on I2, which is the interest rate, assuming 6 months, the next coupon is due 6 months from now. But here the next coupon is due probably when I am purchasing this bond on 18th November, then from 1st June, so many days have already elapsed. So I have to adjust my present value to meet that particular period also. Adjusted present value is nothing but whatever the PV I got as on the date of the previous coupon payment, I multiply it with 1 plus I to the power whatever are the number of days. So from 1st June if I take, okay, 1st July 30 days, 1st August 31 days, 1st September 31 days, then 1st October 30 days, and 1st November, right? By the time I am reaching my 1st November, then there are 31 days and another 17 more days for for 18th November. So basically this entire thing is working out to 93 plus 60, 153 plus 17, 170. So this I have to multiply by 170 by 365. I have to raise this PV by 170 by 365 power, so that I will get the present value as on 18th November, the day on which this is purchased. So I'll take this PV, I say multiply this with 1 plus I to the power 170 by 365, because that 59.05, the formula is for the present value of the perpetuity, assuming that the next payment is is matching with the I which I have taken. If I have taken an annual I, the next payment is expected after 1 year. If I am taking a semi-annual I, then I am expecting that the next payment is due after 6 months. But here I have taken a semi-annual I, but the bond, the investment was made on 18th November, which is just around 12 to 13 days away from the maturity date. So from the next coupon date. So that is the reason we have to adjust. First we will find out the present value of the perpetuity as on June as on June 1st itself, but because we need it on 18th November, we'll compute the number of days from June 1st to 18th November, and then multiply it and multiply the earlier present value with this 1 plus I to the power 170 by 365, which will give me that the present value as on 18th November for this perpetuity is around 61.46. That's the way we work out, or 61.47 is the present value of the perpetuity. So two things here. One, we are looking at finding out the present value of the perpetuity, which is a straightforward kind of a formula. But if the dates are different, we are adjusting the present value of the perpetuity by compounding it using the effective rate of interest, by compounding it up to that particular time period. That is how we compute the present value of a perpetuity. Alright.